the data structures and algorithms course might have or must have required you to do some programming, right? So that will come in handy. So I'll ask you to just brush up some of the programming things, because we'll be doing some programming in this course. And we'll be talking about operating systems. So we'll be seeing what functionalities they provide and so on. So basically, what do we do on a computer? So if that is the question which is asked. Okay, see. We run programs, right? Okay. Thing is. So, and how does a program get executed? So what all happens when a program gets executed? What are the steps needed for a program to be executed? Anybody? Like, you can just, this is just the beginning class and we are just getting a feel of things, that how does it happen? So when you run a program, or when you open a program in your, let's say, computer, what are the steps that happen in running actually the program? Okay. Any ideas? Or, I mean, of course you have an idea, but please, like, let's make the class as interactive as possible. So please speak. Anyone? What happens? So the program is somewhere sitting in the memory, and then where does the running happens, or what does it mean to run a program? A program has some instructions. So those instructions have to be brought.
I mean, didn't we have instruction fetch and operand fetch?
Exactly.
Execution.
Yeah. Good. So the first step. So what happens when program runs? So first is going to be fetching, fetch instruction. Okay. And then what will the processor do after fetching the instruction? So this is TCH, I hope. It will decode it. Okay. So the instruction will be whatever in binary form, and then the processor will figure out what does the instruction mean. Okay. And then it will execute it. And what does it mean to execute? It might be something like add numbers, or access some other memory. So fetch instruction from memory, right? Or any of such things, right? Now, whenever a program runs, a lot of things happen. Okay. And then we still want to, make it usable. So we don't want to look at the processor whenever we run a program and we see what instruction it wants to, what instruction it's fetching and how to decoding and executing it. That's the work of the processor, and so on, and where in the memory the things are. So the operating system gives us an interface that makes the things easy to use. Okay, and so this is what, like, this is the main, like, purpose of the operating system, that it wants to make things easy to use for us. Okay, now how does it do that? Okay, so first thing is, so it does many things, like sharing the memory between programs. Or interact with devices like speakers, keyboard. Okay. And one of the key things that the operating system does, so I'll be using OS and operating systems, like, interchangeably. So one of the key things that it does to make the system easy to use is called virtualization. So anybody has any idea about what virtualization is?
It makes the program look into the memory as if it was all of its own.
Yes, so that is what is the effect of. So that's correct, that it does happen, but that is one of the effects of the virtualization process. That it would make the program look at the memory as if all of it it is available, all of the memory is available to the program. But what is virtualization itself? Like, what would you call virtualization? So virtualization is just taking some physical thing and, like, uh, making a virtual form of it, and making a more general virtual form, and that is what then any process or the user will interact with. It will not interact with the actual machine. Okay, so then the OS will create a virtual form of the memory, of the processor, of devices, and that's what the programs or users will interact with. So what is virtualization? So take up a physical. Okay, this thing is. I hope I'll get, like, something new to, something better to write, so that it's not as bad as this thing. Take up a physical resource like processor, memory, disk. Okay, and transform it into a more general virtual form. Okay. Okay. So that is why your operating system is also called a virtual machine. All right. So it provides some things like this thing called application programming interface. And we'll see what these things are throughout the course. In short, they are called APIs and system calls. Okay, so we'll also see what these system calls are. So these are some ways through which programs can interact, programs and users interact with devices. Okay. And this virtualization is what allows many programs to run simultaneously. Okay, good. So now let's see what does the OS like, or how does it virtualize, these things, and what does it mean for virtualizing the, resources. So we'll see two of these in detail throughout the course, or actually all of it. So first part is going to be, so the book is called Operating Systems 3 Easy Pieces, right? So the three pieces are going to be, so the three pieces are going to be virtualization, second is going to be concurrency, and the last is going to be persistence. Okay. So in virtualization, there will be two parts. First is going to be virtualizing the processor. Okay. So we see that always, even right now I'm writing on the, this OneNote thing, and, Microsoft Teams is working in the background, and my browser is also working in the background, and so on. And right now I'm speaking, it is recording my voice, and there are many processes that run. Like you can listen to music at the same time and while work, even if your computer has only one processor, right? So how does that happen? So how do many programs run at the same time? On a single processor machine? Okay, so this is a question that we'll be answering. So of course, since the processor is single, of course it cannot be that they are actually running all at the same time. So it is an illusion created by the operating system. Illusion. And how this is achieved? It is achieved by virtualizing the CPU. So as I asked the earlier question, and there somebody said that it was about virtualizing the virtualization was about the memory that every processor thinks, every program thinks that it has the memory all to itself. So yeah, okay. So I hope you have seen, or if you have not. So what is a process? It's a program which is being run or program being executed. We'll see in detail what these things are going to be. But a program is a passive entity and a process is an active entity. So there are going to be more things associated with the program which will be in the memory when a program is being executed, like which instruction is to be fetched or processed next, and then like some data with the program and so on. So there is this differentiation between process and program. But if it does not make like too much of a difference, I might use them interchangeably sometimes, and the context will make it clear that what is the meaning. Okay. Okay, good. So virtualizing the CPU, and all processes believe that they have CPU to themselves. Okay, good. And we will need, but then again, the user needs some API to tell CPU which programs to run. To run or stop. And we'll see those. And we'll also see that, if two programs are competing for resources, which one should get? So this is decided by operating system policies. And we'll have a look at those also. Okay. So this was about virtualizing the processor. The second thing, as I said, is going to be virtualizing memory. Okay. So what is memory? Memory is just an array of bytes, right? And there are basically two operations, read and write on memory. It is going bad. So what do we need for read? For read we need a memory address. So this is array of bytes, right? So every byte has its own address, let's say, or array of words, if not bytes. And I hope you will be familiar with the differences, that whatever the smallest addressable unit of the memory is, that is called a word. And then every word has its own address, and then you need the memory address to read it. And for writing, you need memory address, plus you also need data, that is what to write at that address, right? So these are the two basic operations which are performed on the memory. So what happens when we run programs, right? So every program will, so first thing, even the program resides in a memory. So even to run the program, which does not have anything directly to do with the memory, we need to load it into memory. Okay. And then we need and then we perform some maybe arithmetic. Okay. So then we perform the instructions. Okay. In the program. So now every time an instruction has to run, every time it has to be fetched from the memory. Right? And even if the instruction is not about memory itself, still even to bring the instruction, you need to access the memory, right? And then the program might have its own data. Which and if the program wants to do something with its own data, then that data has to be fetched and so on. So for that, every program will have its memory space. Something called memory space. And for all the processes that starts from 0, right? And then whatever. You can add things here and then that's how it goes. Okay. So, so suppose this is your actual memory. Okay. And the OS is residing here, and then suppose this is the process 1, this is process 2, and then what happens is that, okay, so then even though, so this is the actual memory 00 something, this is something, let's say 1001 to 1999, then this is, or let's say 1001 to 2000. Then suppose this is 2001 to 3000 and so on. The actual memory. So this is physical memory, right? But when this process looks at its memory space, then memory space is going to be from 0. Even this process's memory space it's going to be from 0. So this process does not know where it is residing. So this job of translating a process, an address in a process's memory space to a physical space is done by the OS. Okay. And because of this virtualization, what also happens is that a process can only see its own memory. It has its own space. So it can only address things into its own space, right? It cannot address, because it whatever address it gives, the OS will translate it into its own physical space. So a process can never address a location or never use a location in the physical space that belongs to another process. Okay, and this is possible because of virtualization. Because otherwise, if the processes could uh, like access any memory location, then they can write here. If process one knew, if the only call was to just go to some memory, write something, then process one would come here and write something, or it would go to even OS and write something, and then the whole thing will be corrupted, right? So we do not want that. Okay, another.
Sir,
Yeah,
I have a question.
yeah, please.
Uh, isn't this allowed if the process is running as a privileged process?
So we'll come to that. So if the process is running as a privileged process, so actually what happens is there are system calls for that, and generally what happens, like in most cases, is that the process will ask the OS to do these jobs for it. Okay.
Okay.
So the OS is the privileged process, is the most privileged process, and it has control of everything. So there are these system calls through which control is transferred to OS, or it goes into kernel mode as it's called. And then when the system call is executed, so this is done via trap, you'll see these things. And when the call is executed, so the OS does the job on the process's part, and then it returns the control back to the process. Okay. So that is how typically things are done, and generally processes are not allowed to make changes into memory or in the memory space. Okay.
Yes, sir.
Okay, good. So the next theme, so these were the two virtualization things. So first was virtualizing the processor, second was virtualizing the memory. And then the second theme, as I said, was concurrency. So we know that many processes run at the same time, but using system calls, as we just discussed, they might want to modify some memory, or even within same process, let's say. So there is this thing called threads. Okay. And suppose there are two threads in the process. So threads are just sub processes that run together. And we'll see how to give rise to like how we can make use of these. And they can share some memory space and so on. So suppose there was a variable and you write two processes, two threads, which are, so let's say this says that 10,000 times increase the variable. So let's say the variable is called var. And P2 also does the same. Let's say the other thread 10,000 times increase var by 1. So there is an example in the book. You can run it and see for yourself that what happens is that at the end of the process, you'd expect the value to be, let's say, 20,000, because 10,000 times it will be increased by P1 and 10,000 times it is increased by P2 and so on. But what happens is that increase the variable by 1, this statement is actually not an atomic statement. It is not, it actually takes three things. Okay. So suppose wherever var is, so suppose this is where var points in the memory. So this is the whole memory. And this is a register where in the CPU, where the increment will take place. So first step, this has to be loaded into CPU. Okay. Then it will increment. And then it will be copied. So it is a three-step process, right? So why the actual value might not be 2,000 sometimes or less than 20,000 most of the time actually is because what will happen, one process has suppose loaded, okay, and is incrementing. But till now the previous process is still here. So suppose the value was 535 and then this process loaded this into 535. But before it could copy anything, the previous process, maybe it was at like the other thread is at 500 only. Okay. It wrote 500 here. And when this one got done, it wrote 536. But then the previous one will get done. Suppose now it did a cycle, then it will do 501 because it wrote 500, then copied 500 here, then incremented it, and then did this, then increased it. So what happens is that there are three instructions and they might not execute together. This increase the variable by 1 is not an atomic instruction, and because of that, the process can interleave, and because of this interleaving, you might not get the desired result. So how to take care of such situations? This is what we'll see in when we'll talk about concurrency. Okay. Okay, good. And then the last part that I said was persistence. Okay, so what is going to be, the memory, this memory that I keep referring to is the dynamic RAM, okay? And this is volatile. And what does it mean for it to be volatile? When power goes off, all data is lost. Okay, but then we do want to store data. Right? So, and we want to do that persistently. That means, or for long term. Okay, so for that we generally have a disk, right? And and the program that manages the hard disk is called file system. So this is part of the OS. Okay. And why do we need a like program, and what is done here? So first thing, like why doesn't the OS, just like it virtualizes the memory, it does not virtualize the file system also? And for each process, it will make its own, like let's say file system and its own memory, virtualized memory, and so on. So why would we not want to do that? Anyone?
So it would be too huge in size.
Too huge in size, but it's virtual. So just like the memory, if it is huge in size, that like the file system, it's virtual. So that is not the main problem here. What do we use files for generally? Or what is the main idea of a file? It's an entity we would like to move around, right? We would like a file to be opened in like many different applications and so on. So shareability of a file is a very like fundamental desired feature, or that is we can even say that one of the basic things about a file, that we want it to be shared across many different programs. So in that way, it will not be useful if we just make a program, its own virtual memory and make the file only in its own memory, because then it will be hard for it to share. So that is why the OS uses the hard disk, and that's where it. So individual virtual spaces will not be a good idea. Why? Shareability will be hampered. So my MS Teams just said there is bad network quality, but still you can hear and see what I'm writing, right? Yes.
Yes,
Yes,
sir.
sir.
Okay, good. Okay, so we'll see how the OS manages the files, how the file system manages the memory, and what kind of things we'll employ to do these things. So, like for example, these system calls like open, close, or write, what they mean. So these are system calls which the OS provides for applications to open a file which of the file system. To manage the memory, okay? And how does the OS write to the disk? So it talks to these things called device drivers or disk driver, which interfaces, and but then the program or the user should, it should not be necessary for the user to know how the device works or how things are done there and so on. So OS talks to the device driver, okay, and for the program, for the user, it gives a standard library of functions, right? Like open, close, right? Okay. Now we'll see that we'll see about how to write things persistently. What happens when an error occurs during write, or how do we recover that? Etc. Okay, and some data structures. For file systems. Okay, so this is what the course will cover mostly. Okay, so first theme will be concurrency. First thing will be virtualization, which will be virtualizing the processor, virtualizing the memory, and then we'll see concurrency and how, the problems arising with concurrency and how to take care of those. And finally, we'll see how do we store data on a disk, okay, persistently. So these are the three major themes, and this is what an mostly job of an OS. I mean, there is some other security stuff also, which we'll not be discussing. That is a separate course by itself. So now, like quickly, when somebody is designing an OS, what are the design goals of an OS? So first is going to be abstraction, right? Which allows virtualization and so on, okay? Or virtualization is a form of abstraction, so that one does not have to see all, know all the details, right? Like when you write in C, you don't actually care how the program is going to get executed, like at the very microprocessor level. That when you just write, as I said, we just wrote like, a variable plus plus, and then like, how it's going to be, we don't really care. So the OS provides that abstraction, but while providing that abstraction, it still needs to be careful, right? Another thing is performance. So all this abstraction and virtualization needs some more. So abstraction, virtualization would take more memory or instructions than what, like if we just run a raw program, memory or instructions. So we would want, so this is called overhead. And we would want to keep it to a minimum. if not 0. Okay. Third design goal is going to be protection. A process should not harm other processes or OS. Harm okay, and we want the OS to be reliable. That is reliable, running at all time, and taking care of errors, etc. Okay, now it's malfunctioning a lot. And then you might have something like energy efficiency, security, as I said, but we'll not be discussing that much. So security is about, some malicious people trying to, some in network or so on, and then they are trying to get to your computer and do something. And last one is mobility. That you want your operating system to be usable on range of devices. Okay. Now it depends on what kind of operating system you are designing, and so these are the general goals. But depending on what kind of operating system you are designing, you might want to, maybe you don't want mobility because you just want to use your system only on one device all the time. Okay, maybe you don't want like so much security because you are not going to get connected to any networks and so on. But generally, all these are like good practices, and OS, or performance. Maybe if you have a supercomputer, if you have a little bit more overhead, then you don't care much about that. But generally, these are the design principles, and some trade-off between these will go into any designing any OS. Okay. I also wanted to talk about the history a bit, but I think we are out of time. And you can just go through the history that how the first computers were, and you might have seen that in some earlier courses and so on. And my pen is also gone, it seems. So, history, the first was like batch processing. Right. Or before that, just libraries actually. Basically, earlier computers did not have like any OS at all. They would just have some standard, okay, if you want to addition, then there is a function for addition, and that's all you can use, and so on. Then and every person would do it one by one, their job. But then they said, okay, if we do it one by one, then there is a lot of time lost. There is a lot of problems that happen. That I mean, a lot of resource wastage is happening because people take their own time and so on. So then they started this batch processing. That okay, in one go, many people's job will be done. Then came the concept of like system calls, as I was telling, and which give protection. And then came the era of, let's say, multi-programming, where now many programs could run at the same time. And then came the PC, personal computer. And then personal computer at first did not really use this, the system calls and protection. Like very famously, MS-DOS, the disk operating system. I mean, you guys might not know, but like, when we were younger, it used to be the thing. And there used to be these blue screen of death in earlier Windows things, and once that happens, then nothing can. And why did that happen? Because the processes could write in even on the top of OS. So there was no system calls or separate privilege for the OS. As I said, that here the OS is going to have some more privilege over the processes. So it can have processes don't have the right to write anywhere on the memory. But in MS-DOS, for example, they had that. But now all the like Unix, Mac, which is Unix based, and even Windows, from Windows NT, they started having these system calls and so on. So they all have system calls, and which gives the protection. So that is just some history, and like, yeah, I just spent 2 minutes on it, but you can read more from various sources. The book has like, some small notes on the history, and it has more on the Unix, like how Unix was developed and so on. But yeah, that's, I won't be talking more. So in the next lecture, we'll be talking about process, and we'll start with the first thing, that is CPU virtualization, and we'll be talking about processes and how processes are brought into memory and so on. Okay, so that's it for today. Thank you all for coming in. Any questions about the class or anything else? Quickly.
So can I be added to the teams?
Okay.
I'm not a member.
Okay, let me just do it. So
Thank you.
Could you tell your name again?
My name is Hetvi Jethwani. And my
Okay, yeah. So wait. Hetvi. Just give me a moment. Can you raise your hand again so that it will be easier for me to find you? Hetvi. Okay. Good. Hold on. Okay, I don't see that. Okay, any other questions till then while I'm trying to add Hetvi? Okay, no questions. I see another hand raised. Udharsh.
One second. Yes, sir.
Yeah, do you have a question?
No, sir.
Okay, so your hand was raised. I thought you have it. Okay,
No,
Hetvi,
it might be by mistake.
okay, no problem. So I'm not able to add right now, but I'll try to figure it out. So this is a bit new also to me. And yeah, anything else? Any other questions?
So we also have a lab slot. I mean,
Yes, so there is a lab slot, and but we'll need to figure out. So how do you want to do it? I was thinking that since we are in offline mode, you try things on your own, and then one day in a week or something, you can sit with the TS and me, or we'll see how to, and you can ask doubts instead of sitting and doing. I think this might be better. That
sounds good since we have assignments anyways. I think that sounds like a good idea.
Yeah. So yeah, so the assignments will come slightly later, because right now I've not really taught anything that I can give you any assignment, but you can just start brushing up some basics from your data structure and algorithms course, and just going about. Okay.
So just to clarify, I mean, we don't really need to attend labs as such, right?
No, there is no attending lab as such.
Oh.
But you'll need to submit the assignments, and there will be sessions with the TAs where you can ask questions.
Yeah.
Okay. Is that fine with everyone? Because I don't think it makes much sense for having lab sessions online. Okay. Okay. So yeah, some of you might have another class in like 3 minutes. So I'll leave you. And if you have any questions or anything, you can send me an email. The web page is running. You can search my name, and my name is Ashutosh Rai, Ashutosh. Okay, it's there in the members list also. And I have a web page for the course, so you can see the information there, and you can send me an email as well if there is any problem. Okay. Thank you, everyone. Shubhalingam, do you have a question?
Yes, sir. So regarding assignments, is there any specific language or something that we are going to follow, or you can use any language?
It is preferable to do it in C. So C is the like most basic thing, and we'll be doing like mostly things in C. So
Okay, sir. Thank you.
yeah. Okay. So thank you, everyone. I wouldn't take any more time. Thank you.